Hey, how are you?
Hey, what's up?
Not much.
How you doing?
I'm good.
All right, that's good.
So, yeah, what class is it? Is this chem?
Yeah,
Okay, cool.
straight up Gen Chem 2.
And is it okay if I record this for the YouTube?
Yeah, go ahead.
All right.
It's never an issue with that. You have my consent going forward,
Okay.
unless I say otherwise.
Mhm. How was your trip?
It was okay. It was pretty good.
Where'd you go
Wasn't
again? You went to
bad.
like LA or something?
No, I went over to see my girlfriend in San Diego,
Oh, cool.
and then we took a road trip to Las Vegas and Arizona,
Nice.
so I could meet her grandparents on both sides and just hang out so she can show me the West because I've never been this my farthest west I had gone to Chicago, so I've never gone to
Yeah,
California or
yeah.
anything.
I think my farthest west was like Tennessee.
Yeah. I went to Tennessee earlier
Mhm.
in the summer.
It's cool. How'd you like the West Coast?
The West Coast is really nice.
Yeah, they get a dry heat.
Uh,
They get a dry heat,
yeah, they get a
unlike
dry heat.
us.
It's not humid.
Yeah,
However,
yeah.
Arizona was very humid because it's monsoon season over there.
They what? They
Yeah,
get.
they get like
I
heavy
thought
torrential
they're
downpours.
like. I thought it was like all desert.
Yeah, it is all desert, but like there's a certain 2 months out of the year where they'll get
Okay.
like rain 3 4 times a week and it's torrential downpours.
Jeez.
So it was 101 on top of like 85% humidity.
Mm-hmm. Damn.
Disgusting.
Yeah. It's. I think like a very tiny part of Arizona is actually habited, like inhabited. Most of it is.
Yeah.
Most of it is just like uninhabited
Well,
desert.
my girlfriend was telling me she used to live there until she was like 16. That's when she was in San Diego. She was saying that like um what do you call it? A lot of the land there is preserved by the like federal government
Makes
and
sense.
stuff
To make
because it's so
bombs.
old.
Oh wait.
And the
No, that's. I'm thinking of Los Alamos in New Mexico.
Nah, yeah, she says that a lot of it is protected by the federal government and the state government, so no
Yeah.
one can build on top of that.
Mm-hmm.
Because a lot of the cacti there are over like 600 years old
Yeah.
plus that are growing, and
Yeah.
there's fields of them, so they refuse people to cut down.
Yeah. That's nice. I also think it's probably it would be hard for them to start building property there. They would have to like funnel a lot of uh, water from like northern California. That's
Actually,
how like
all the
Las
water
Vegas was
that,
made.
yeah, Las Vegas, I mean, Nevada, California, and all of Arizona.
Yeah.
All three of those states in totality are run through the Hoover Dam, so they need to run a line from the Hoover Dam there.
Yeah. Yeah.
I went to see the Hoover Dam too.
How's that?
It was nice, and I saw the
Mm-hmm.
Grand Canyon. It's pretty
Oh,
cool.
cool. Yeah. Did you know all the humans on Earth could fit in the Grand Canyon?
Really?
Mm-hmm.
All 8 billion of us?
Mm-hmm.
Wow. I mean, I wouldn't knock it because it is huge.
Yeah.
Uh, my chem teacher hasn't answered anything. She said she wanted to talk to me like June on July 22nd or whatever,
Uh huh.
saying because I hadn't done any of the work because obviously I was sick and stuff like that,
Mm-hmm.
and I've still been sick even on my trips and
Yeah.
whatever that I wasn't able to do work and whatever. And she told me that what do you call it? It was fine if I needed to take my time to finish until like the end before the beginning of the fall semester and stuff. And then she came out of nowhere saying that she was like gonna threaten to fail me or something like that. And I was like, wait, what? She told me I had till the end of summer to finish.
Well,
So
like
then
you
I've
don't
been trying
have
to meet
any,
with her.
you don't have anything due until like the 16th, right?
Yeah, exactly. And stuff. And she was like threatening to fail. And I was like, what are you talking about?
Mm-hmm.
And then I've been trying to contact her since the 23rd, and she hasn't answered anything.
Yeah.
And she sees my messages because it shows that she's seen them.
Yeah.
And I'm like, what? I just tried
Mm-hmm.
to book an appointment to talk to you, and then you saw the message and then ignored it.
Yeah.
But,
So you know, okay. I mean, yeah. Just if there's no like deadline other than the 16th, you can get everything done by the 16th. Like,
yeah, but then there's another issue because there's this class is graded out of 1,200 points
okay.
and stuff, and all that she says that's graded out of and whatever, when I did the math, only adds up to 815.
Okay.
I'm like, where's the extra work that makes it 1210? Because then
Yeah.
that's the highest you can get is a C plus
Yeah. Yeah.
in the class. She hasn't answered anything.
But you don't have like any like what? Yeah. What's the work that needs to be done? Like exams or?
It says you have available to gain you points Alex lessons,
Yeah.
which is like close to 60,
Mm-hmm.
and they're 5 points each. The Connect readings, which is 54, there's 5 points each too. The Connect quizzes and projects, there's only 3 quizzes that I see there, and then the projects are like 12 of them, and they're 10 points each.
Mm-hmm.
So that's 150 there.
What are
and then the
the
Alex
projects?
quizzes, there's 11, so 110 points there.
What were the last thing? What's the last thing you said?
The Alex quizzes are 110 points.
Oh, okay. So the
There's
quizzes.
11 of them.
There are quizzes on Alex. There's what are the projects? Are they like lab stuff?
They're like they're 5 question mini quizzes, and most of the times you can find the answers online, so they're easy to finish.
Yeah, yeah. So let's see. But they're like free response.
No, they're multiple choice.
Okay. So yeah, what do you want to work on today?
Alex, just give me a second.
Mm-hmm.
Getting her another thing before I forget. If she doesn't answer by tomorrow, I'm gonna contact the head of the chem department. I don't know the choice.
Sorry, say that again.
I'm gonna send her another thing, and if she doesn't answer by tomorrow, I'm gonna call the head of the chem department.
Yeah.
Because I'm not getting any answers, and I need them if I have 20 days to do this.
Yeah, yeah.
Okay. Share screen.
So did you watch In the Heights in the theaters?
No, I saw it on HBO Max with my girlfriend.
Okay. Yeah, it's no longer on that, but I'm going to see it in the theaters with my girlfriend because it'll be pretty cool going to a theater again. And yeah, I've just listened to like that extended intro on YouTube and then that tiny like blackout scene. because I don't want anything else to be spoiled. But it's like I've been listening to it on repeat like so much.
It's really
it's
good.
ridiculous. I think Lin-Manuel Miranda's a genius. He's like it's ridiculous how like, and also I really like the that guy. I think his name is Anthony Ramos. He grew up in he grew up in Bushwick.
Yeah, and he's he plays one of the main characters on the play Hamilton in Broadway.
Yeah, that would make sense because Lin-Manuel Miranda did Hamilton.
Yeah.
Yeah.
A lot of the guys in there are from Hamilton.
Yeah, it's so good.
Yeah.
This stuff again. I remember. I hope we don't see any significant digits things again in my life.
Oh, probably gonna happen again.
Okay. Wait. Suppose the song is held at -1 and that. Oh. Okay. It's crazy because I've been like going on like physics binges, learning about all these other types of phases of matter.
Okay.
But I'm ready when you are.
All right. Just gotta get 2 of these right. See.
Suppose a small sample of pure X is held at 15 degrees Celsius, which is we gotta convert it into Kelvin. Remember?
Mm-hmm.
So that's just gonna be 280. 280.
You mean 279?
No. 273 plus 15.
73.
288. 288 Kelvin.
288 Kelvin. Okay.
So let's see. That's
Like
300,
right
so it's like there, and then pressure is 10.5.
So it's a liquid.
All right.
Okay. Now 280 plus 15. I mean 273.
7.9.
15.
Well, it decreases from 10. Okay. From 10.5 to 7.9.
$2.6.
So gas, right?
2, 4, 6. Yeah. So it'll be gas. It will.
Oh, boil? I mean, yeah, liquid to gas is boil.
And then suppose on the other hand the pressure is held constant at 10.5, but the temperature is increased by 95 Celsius. So if we just go 288 plus 95.
368.
383 is what I got. Because it said held constant at 10.5 ATM.
Wait.
The temperature didn't change.
The temperature is increased.
Yeah.
By 95.
Yeah, but like the base temperature didn't increase from what I saw. I don't know. I think it'll be the same thing anyway. But
wait. Oh, sorry. Wait. So 288 plus 95.
95. Yeah.
So that'll be
383.
380. Yeah.
And then 10.5. So it's going to be a liquid again. So
nothing.
Check.
Yeah.
Yeah.
Cool.
So -120.
That'll be 153.
So that's just
153. Kelvin.
Yeah. So 153 kelvins. That's like down here.
And 2 atm gas, right? Oh wait, now it's a different
No, it's
scale.
gonna be a solid.
Yeah, it's a different scale. Okay.
So suppose the temperature is held constant, and at that, but the pressure is decreased by 1.3. So that means it would be 0.7.
Mm-hmm. So half of that 1.4 I'm on,
Yeah.
it's still solid, right?
Yeah, it would still be solid, nothing.
Mm-hmm.
The pressure is held constant at 2 atm, but the temperature is increased by 297. So 153 plus 450. So that's like, so it's like right here.
Mm-hmm.
And it's held constant at 2. So it's like here, it's a liquid. So it's going to melt.
Yep.
Check.
Yep.
Nice. 259.
I told you my nephew that was just born is has the same name as you, right?
Oh, yeah.
Yep.
That's right.
Noah.
Yeah.
How vapor pressure of three liquids varies with temperature. Pyridine. Okay. Which liquid is so volatile means it has it can go into the vapor phase more easily, so it's gonna have a lower it's gonna have a higher vapor pressure.
Oh, okay.
Okay, yeah, and that's just talking about it. So like, yeah, naturally things go into the vapor phase. Yeah, so it says volatile. Yeah, okay. So most volatile is the one with the
Lowest vapor pressure.
that should be the one with the highest. Because vapor pressure is just liquid going naturally to the vapor phase, like gas phase, but not boiling.
Mm-hmm.
So like alcohol is considered volatile. That's why when you use like a hand sanitizer, it like disappears.
Yeah.
And then they
Okay.
said normal boiling point of each liquid. So so that would be the boiling point is when it's equal to the uh, atmospheric pressure, which is 760 torr.
Yeah.
All right, and then what's the speaker question?
Put inside a sealed tank containing that at 140 degrees Celsius and 677 torr. It determines there'll be more liquid in the beaker, less liquid, or the same amount.
Oh, so they're not changing anything. So like they're not
Yeah.
adding. Yeah.
Okay. Ready?
Yep. Most volatile, piperidine. Least acetic acid. Wait, I can't even. The black one, ethylbenzene. I had to take off these tints on my glasses to notice that.
Oh. What is the normal boiling point of each liquid? Know your answer must be within 1 Celsius. The exact answer.
Yeah, so we gotta look for where 760 is on the vapor pressure thing. Yeah. Oh, cool, it does that?
Yeah. Boiling point of each liquid. So where would we find that?
Oh, so like
Once it gets to 760, right?
yeah, 760, that's going to be that like third notch, right? I think. 1, 2, 3, 4. Yeah, so 720, 740, 760, 780. It should be the third notch. That one, right?
Yeah, that
Okay.
one.
Boiling point of each. Oh, we gotta do each of them. All right. So that and. Oh my god, we have to count this. Okay, because we have to be within 1 degree Celsius. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9.
Yeah, it's
Oh, okay.
136 degrees Celsius.
Yep.
Okay.
All right.
So piperidine is once it reaches 760, so that's the third notch. That's gonna be 106.
Okay.
And then acetic acid, so third notch here, there. 118. Suppose a bigger vat, put inside a still tank containing gas at 104 degrees Celsius and 180 and 888 torr at the temperature, so there any more liquid, less liquid, or the same amount. So if we go to 104, which is here, then we go to 888 torr, which is
like a little above the fourth notch after the 800.
Yeah. Yeah, like that. But it doesn't let me go over. See here?
Oh,
just fine. So
yeah, you can go just. Oh yeah. So yeah, it's not gonna match up with the red thing, right? So it seems like it'll be like whatever, because it's above that. So it's already gonna be boiling, right?
Yeah.
But there should be less liquid.
Row 3, your answer is incorrect. So would it be more liquid if it's boiling?
Oh, it's wrong? Damn it.
Piperidine is green. So
yeah, okay. At 104 and then that high, it's definitely boiling. If it's sealed, then maybe it's the same. That's pretty.
Oh, if it's sealed, maybe it is the same then. Because if you think of it when something's boiling,
It'll
the
reach the
evaporation is just creating a condensation reaction at that point.
Yeah.
So more liquid is being formed at the top.
Yeah. Okay.
Let me check it. Let's see. Damn, it was more. Oh. Wait, how's that?
Okay, so recaptured by the liquid, vapor will condense, amount will grow. Okay. So okay, fine.
Well then, this stuff's easy though. So what's in this volatile? We're gonna go with cyclohexane and dimethyl sulfoxide is lace volatile.
Yeah, this part's annoying. Okay. What is that? 189. This is like such busy work.
What?
This is like such busy work. What is that? 161 or something?
Yeah. And cyclohexane is 1, 2, 3, 4, 5. Suppose a beaker of cyclohexanol is put inside a sealed tank containing cyclohexanol gas at 152 degrees Celsius, 551 torr. So 152 is here. 551 torr is like here.
It's a little, yeah, it's like a little higher, I think.
Mm-hmm.
Or wait.
At the 10 minutes, will it be more liquid on the beaker, less liquid, or the same?
So, is it above that line?
Huh?
Is it above that line? Oh, it's on the line? Or wait.
551 is like right here. 52.
Okay, it seems like
It's like right there.
on the line, right?
Yeah.
So
So
is
it
it
should be the same?
I think so.
Hope so.
Okay then.
Yes. So.
Okay.
Methanol,
Yeah.
most volatile. Isopropyl acetate, least. Methanol is 60. Right there. 1, 2, 3, 4, 5.
Is it 65?
Yeah. Benzene. Let's go over to the 60 mark. Boom.
Looks like it's
80.
straight up 80.
Yes. And the isopropyl acetate right here.
89.
89. So suppose a beaker of benzene is put inside a sealed tank containing benzene gas at 75 degrees Celsius and 854 torr.
Seems like it's going to be less. Because it's like above that line, right?
So there's 75.
Oh wait, sorry. So like if it's like the opposite of what we thought, right?
Yeah.
So more, right?
Yeah. You suck.
So yeah, the red line is only going to go along those curves, but yeah, it'll be like above it.
Yeah, it's gonna be like here.
Yeah.
Where my mouse is.
Mm-hmm. So if it's above the curve, it's going to be making more of the liquid because it's counterintuitive like that.
Yeah. Oh, check.
Yeah. All right.
Next. Sending connection between vapor pressure, boiling point, and what? And enthalpy of vaporization.
Yeah.
Okay.
So let's see. So basically, all right, 82C, it has a vapor pressure of that, and D has a vapor pressure of 108. So I think there might be an inverse relationship. Let's just like look at the thing. Let's see. Higher enthalpies shifted down and to the right. Vapor pressure at any, okay. So we just look at the answers and
Marvin?
sorry. Yeah, you can go see the answers and then go from there. Let's see. So let's see. The thing.
Alright, so it seems like lower vapor pressure means the higher the boiling point.
Okay. And
At
then
1 atm, substance A spoils at 36. Substance A is not bad. Higher vapor pressure is going
lower
to
boiling
be
point. So
B.
vapor pressure and boiling point are inversely correlated.
Yeah.
And then let's see, enthalpy of vaporization. So the thing that has the enthalpy of vaporization is proportional to. I'm just gonna write these in the chat so I don't forget. So we got vapor pressure inversely proportional to boiling point, and enthalpy of vaporization is proportional to boiling point. Good to go?
Yeah. Right?
Oh. Okay. So remember, boiling point and vapor pressure inversely proportional. So the thing that has the higher vapor pressure will have a lower boiling point. So that'll be substance D.
Okay.
Enthalpy is proportional to boiling point. So substance B. And then we have oh wait, and then I forgot to relate enthalpy of okay, so I could do that because I know that enthalpy of vaporization is proportional to boiling point, and if vapor pressure is inversely proportional to boiling point, that means enthalpy of vaporization is also in proportional. I'm sorry, is inversely proportional to vapor pressure.
Okay.
So the thing that has the lower the thing that has a lower vapor pressure will have a lower boiling point, which means it'll have sorry. What am I talking about? So the thing that has the lower vapor pressure will have a higher boiling point, which will mean it has a higher enthalpy of vaporization. So substance E.
Second.
Yeah. Oh my god, I hate my life. Okay. Let's see. Vapor pressure. So substance E has a higher vapor pressure, which means that it has a lower boiling point, which means that it has a lower enthalpy of vaporization. Why didn't I? Okay, so sorry, my bad. So it should be substance F. That has a lower vapor pressure, which means higher boiling point, which means higher enthalpy of vaporization.
There you go.
Yeah. All right. Enthalpy of vaporization and vapor pressure. So vapor pressure inversely proportional to the enthalpy. So the one with the higher vapor pressure has a lower enthalpy of vaporization. So substance C. Oh, C? Oh, wait. C is bigger. So, okay. D.
Okay.
Yeah. So, okay, vapor pressure and enthalpy. So they're inversely proportional. So the one with a lower vapor pressure will have a higher enthalpy of vaporization. So substance B. And boiling point is proportional to enthalpy of vaporization, so substance E. It has a higher boiling point and therefore higher enthalpy of vaporization. Find the melting point of X when the pressure above solid is 2 atm. So it seems like we just match it with the pressure and see that it's going to be on the line. So that line.
Yeah, and then we do 273 minus whatever it is, or plus.
Oh yeah, to make that final conversion, yeah. All right, at which the melting point, so we're going to look at the solid to liquid graph, is at negative 105.
Negative 105.
So that's going to be
minus 105.
Will it be 273 minus negative? Wait, what am I talking about? Yeah, well, minus 105.
168. So like that. 50, 100, 150. It's like 160 something around here.
Okay. And let's see. 1, 2, 3. So this is 20.
So I want you to find the pressure.
4, 6. So it's like 2.
Okay.
2 point like something.
It'll be 3 because it's like 2, 4, 6, 8.
Yeah. Okay.
And then like 168 will be around here. So it's like 3.
Yep.
What?
Okay.
168.
Oh, I know what we did. We have to make it on that line that's between the solid and liquid. Right? So we have to go... So we're not going to use this red thing. We're going to go like above it. Yeah. Okay. So yeah, bring that to the one... Yeah, it's going to be like... It's like 7, close to 7 or something.
Okay.
Because we were on the line that would make it go from solid to gas.
From
What the?
10 atm. Solid liquid coexistence curve.
Yeah, I thought we lined it up with that. I guess we were a little too close to 200.
Oh.
I think we were a little too close to 200.
Probably.
That sucks.
Okay, well, now I know.
Alright, negative 152.
At what pressure will a sample sublime?
Yeah, that means it'll go from solid to gas.
$121.
Alright.
So 50, 100, 200, 50, 100, 150. No. So how are the intervals here?
What's up?
I'm checking how the intervals are here.
Oh, let's see. 1, 2, 3, 4, and 5. So there'll be 20th of 100. So 25. Wait.
Okay.
25, 50,
No, that's more.
100. No. What the?
No, it's 40.
40?
40, 80, 120, 160, 300.
All right, nice. Good job. So
So 40, 80, 120, 121 is like here.
okay. And yeah, now it'll actually be on that line because that's the line from solid to gas. So this is going to be 1, 2, 3, 4, 2, 4, 6, 8. So like
2.2.
uh
Or like 2.5.
sure.
Yeah.
Yay.
25 degrees Celsius. Okay. So the pressure, okay, X turns into a gas if the pressure above the solid is 0.17 ppm. So it's like 0.2, 0.46, no,
A little bit.
2.5, 5, 7.5, 1. No, right, 2.5.
You mean
Yeah.
0.25?
It'll be 0.25.
Yeah,
for each one.
0.25, 0.5, 0.75, and 1. So 0.25, it'll be below that. So, like, let's see, that's like,
Like here.
yeah.
So then that's 273 minus oh boy. So then this is 40, 80. No, it's an interval of 5, so it's 50, 100, 150, 200. Okay. So if it's 0.17, so it's 50, 100, and then 150 is here, so I would guess around 140. So
Okay.
273 minus 140. No, wait, there's something wrong with that math. Sorry. So if it says 0.17 remains at the line, right? That's like here, right? You would think?
Like 150-ish?
Yeah.
Wait. Oh, great, crap. So, like, yeah, 150, like, Kelvin, I suppose?
Yeah, it's 150 Kelvin.
Mm-hmm.
So how do we do this? We just go 273 minus 150 to get Celsius?
You do, 270, it's, so 150 minus 273.
Negative 123. Oop, no.
Does that make
There we
sense? 273 minus that gives you 150, right? Okay.
Yeah.
All right.
It's 273 minus this.
I mean, 273 plus.
Yeah, it's inverse. It all works.
Okay, cool.
Yeah.
Cool.
Boiling point is negative 132 Celsius. So 273 minus 132, 141. And then this is going what? 40, 80, 120.
It's going to be
So it's 50.
50. No,
Okay.
125,
50.
150, 175. So it's a little bit after 125.
Wait, what? Oh, hold on. Listen wrong.
Yeah, it goes
So
by.
it's 25, 50, 75, 100,
Yeah.
125, 150. Okay, so here. So then for 141, that's like here.
Okay. And then the pressure
That's
at which the
about
boiling
what,
point. So
5?
that's salt. That's gonna be
Big?
liquid to gas. Wait,
Yeah,
no, boiling point. Yeah, liquid to gas. So you're on the right line, and that seems like what
10.1.
10 atm. Okay. Yeah.
I would guess 10.1 ATM.
All right.
Yeah.
Cool. Sketching. So, what's the question here? Oh, the pressure on a sample of pure X held at that and that is decreased until it sublimes. So, pressure is then held constant and the temperature is increased by that. Draw a path. So, you go to its starting point and then you go down vertically for the pressure part until it hits that solid to gas line.
Oh, okay. Cool.
And then, so yeah, we're gonna draw. Wait, oh, and then it increases temperature. Okay, I get it. We're gonna draw stuff. All right. Pure X held at 1.08 atm and negative 21. So that should be what? 252.
Yeah.
All right.
So 252. That's what.
That's like a
Yeah,
little.
so 250 is here.
So
So
it's
that's
a
like
little bit above that. And then let's see, 1.08 ATM. One, two,
so
three.
what is it? It's point.
So
How are they doing this?
mid part is point
Oh, 3 is
6.
0.3, 0.6, 0.9, and then 1.2. Because then that would be 1.5, 1.8, 2.1, 2.4. Yeah, that makes sense. Okay, so it's 0.3. It's 0.3 per interval going up any TM.
So let's see. 0.9. So it should be like between like the 1.2 and the notch underneath somewhere, right?
Yeah. So 52 would be somewhere like right here, and then 1.08. Yeah, it'd be like somewhere here.
Yeah. So I think you can click it and it'll start. Oh, yeah, we got to do that thing.
Yeah, just below like that, and then a little close.
Yeah. All right, and then
Right.
they increase the temperature until it boils. So we're gonna just do a horizontal line until it hits that you know that curve that's between the liquid and gas.
Which is where?
Just keep going horizontally to the right until you hit that curve. Yeah.
Oh, it's like right here.
Yeah, like directly on it. Yep.
Okay.
So then it boils, and then now the temperature is held constant. The pressure is decreased by 0.44. So 1.08 minus 0.44 should be like point.
0.64.
Wait. Oh, wait. Why does it say that? Placing. Oh, it's a new line. So JK. So we're gonna start this one. Where the second line is.
Uh-huh.
Yeah. and it's gonna go vertically down.
So that's 0.6. 0.64 is like here. And then we just join them like that, right?
Oh, you mean the second point? Yeah. I guess wherever.
Like that.
Wait. You should make that the second line, the first point start there and then end up there, because they might be assholes about it. So yeah.
Oh yeah, you want it like this.
Yeah, so place that.
When I held at the temperature is held constant, but the pressure drops, so it's like here.
Oh, but to the right of that, because that first step is going to the right until we hit that curve. So.
But they say the temperature remains constant.
Yeah. So this is the second.
Yeah.
Mm-hmm.
Yeah. It's talking about the second point.
So that's where we place that first point. Right where that second point. So. Go back up. So basically where we ended up last time is where we placed the first point for this line. The two different lines.
Okay.
So go back up. Like go to where that first line ended. Yeah, that's where you place the first point. Yeah, and then the second point is, that vertical. Yeah.
Like this.
Yeah, that's at
6.4 should be here.
Okay. Wait, why does it still look like that? Alright, fine. Okay, so I guess it didn't matter. Because I was like, why is it an X? I thought it should be like an arrow, but whatever. Who cares? Alright.
Here X is held at that. Minus that. Alright, so 217 minus 245. 28.
28 stupid kelvins. And then
60.
25. 1.27.
2550.
That'll be a bit above, that above the middle of that. Wait, am I wrong? Wait, that middle. So. Because 25, no, 0.5, 1, and then 1.5. So it's like in the middle of that, between the.
Wait, what?
Sorry.
273 minus 245 is 28.
Oh, yeah. I was talking about the pressure.
Oh, okay. So pressure 1.27.
Yeah. So that midline is 1, and that notch above that midline is
1.5.
Yeah, so it should be like a little higher than the middle of the two.
Yeah.
Yeah.
Like right there, right? Oh, it is.
Like a little tiny bit, because it'll be higher than the middle of between those notches, right? Because the middle of the notches would be 1.25, and it's 1.27. But yeah, pretty much.
All right there. Yeah.
Okay. All right. So the temperature is increased until it melts. So we're gonna just go a horizontal line until it touches that curve thing. So right there. Yep. Now,
okay.
Temperature is held constant and the pressure is increased by 1.32. So that'll be 2.6, I believe. Or no. Yeah, 2.6.
2.59.
2.59, okay.
So that means 2.5 is here.
Yeah, it's a little higher then. Yeah.
Five nine is like right here.
Mm-hmm. Yep.
Does that look horizontal?
You mean vertical?
Vertical, yeah, sorry.
If you hold shift, maybe it'll keep it straight. I don't know. That's how it is for other stuff, but whatever.
Okay.
Mm-hmm. Oh god. 252.
Oh, here at 252 Celsius.
So that's gonna be 19, I think.
No, it's positive, so we don't. We add it now.
Yeah, my bad.
So it's 525 Kelvin.
All right. So 500
And
is
that-
the midline between the 400 and 600. And you said 525 or something?
Yeah.
So it'll be the midline, like, so yeah, like.
Yeah, like right here.
Yep.
It's gonna be like right here.
Well. Okay, and then 0.19. This is 0.1, 0.2, 0.3, 0.4. So yeah, you pretty much got it.
Okay, second point.
Pressure is
Until the
increased
sample
until it
condenses.
condenses, so it's just gonna go vertically up until it hits that curve. Does like holding shift help like see if that works to make it completely straight? Even I don't even think it matters really, but
No.
okay.
Okay, so I hit the line here.
Mm-hmm.
Okay.
All right, and then the pressure is constant and the temperature decreased by 122. So we're gonna do a horizontal line going to the left. So whatever value you got, like whatever the 500 something, you've subtracted by 122.
403. And it's basically it's here and then basically like right here.
Yeah.
Thanks.
Yep.
Drawing a heating curve. Oh,
Yeah, Alex sucks. Okay. Alright, so let's see from the information that they give us. We have to do that. Let me check out that info for a sec. Oh, it says it starts at 20. Yeah, let's check out that answer. So they're saying, okay, so it starts at 20, so that's why it starts there. Oh, I need to see what else is being done to it. What the hell? Okay. Let me see that top again. Okay, so let's see. So it starts at 20, heated, so it's gonna go. Temperature's gonna go up at a constant rate until 20 kilojoules per mole of heat has been added to the sample. Oh geez, we're gonna have to do some math here. So 20 kilojoules per mole. So we would do let's see. Oh god. All right, let's look down and see what these guys did. I mean, like, just like, or, like,
Where?
Like, let me, yeah. Okay. So, yeah, go like even above. This looks pretty. Yeah, like basically like where it starts off saying now. Let's use these general ideas.
Mm-hmm.
Like make that the top of your screen. Oh, like the opposite. All right, so let's see.
Oh, there
So
you go.
yeah, so first, okay, so it begins. So it starts off at 20. Okay, and then okay, so we don't have to do that. It just says it's so we're gonna make it the next point be where the melting point is, and oh crap, no, we're going okay. So hold on, I think I'm gonna have to write some stuff down here. Let's see. Boiling, melting point minus original temperature times 35 that 35 that's the heat joules per the heat capacity, I think. Heat capacity to give you something in joules per mole. When you get that, that becomes the new, okay. That's the, okay, x coordinate, and melting point is the y coordinate. Once that happens, let's see. Once down, okay, until enough heat has been added, the amount of heat necessary to melt will be 5. The enthalpy of fusion. Okay, so then, okay. Plus enthalpy of fusion is equal to whatever heat added. Okay, this heat added is a new x coordinate. Y coordinate stays the same. And then the added heat raises the temperature. So then, okay, then it'll be like the boiling point minus, the previous whatever temperature, which is basically the melting point, times, then it should be the that is the heat capacity. Okay, and then that becomes a new x coordinate, and then wait, 22, sorry. Okay, let me see a little bit below that. Okay, and then we do this. Heat enthalpy, okay. Damn it, okay. This is... I'm just gonna screenshot this for reference. Okay. Let's just go to it. This one's gonna be a bitch. Okay. So this guy is going to, okay, it starts at 50 C, heated at a constant rate until 10 kilojoules per mole of heat has been added. So basically, I'm going to take, okay, I'm going to take the melting point, which is 85C, subtract it by the original, which is 50C. I'm going to multiply it by the heat capacity of the... Wait, it starts off... Okay, it starts as a gas. Wait. So this is going to be going down then? Okay. No, wait. Sorry. No, okay. It starts off as a solid. So that's going to be times 39. Okay. Tell me when you're ready.
Yeah. Okay.
So, okay. This, so yeah, we're gonna start at the 0 and 50. Oh, yeah, put this in your calculator.
All right.
Let's see. Uh, 35 times... Oh, this isn't kilojoule? Okay. Alright, 35 times, 39.
Yep.
And then divide that by 1,000.
1.365.
Okay. So that number that you got is going to be the new x coordinate, and 85 is the y coordinate. And you're going to start from, the origin over there.
Wait, where's 85? What are you talking about? Oh, melting point. Okay.
Oh, this is so much easier. Okay, so that first number is the number that you got in your calculator.
Okay.
And the second number is going to be 85. Plot that. Oh, thank God. All right, this makes it so much easier now. All right, we could just do this, and then we can draw those lines at the end, okay?
Okay.
So now it's going to be basically... So, okay. The number you got in your calculator, we're going to add the heat of fusion. So let me see that. Up top. Enthalpy of fusion, okay.
Plus 4?
Yeah.
So it gives me 5.365.
Okay, so that is going to be the new x coordinate, and the y coordinate is going to be the same as before. It's just going to be a horizontal line. So, 85. Good. And wait, do they want us to plot that first point? Might as well. That's going to be, 0 and 50. 0 for the x, 50 for the, y. Nice.
Okay.
All right. Then they're going to add more heat until So yeah, let me see. Okay, until it boils, right? So then it's going to be, so boiling point 135. So 130, do 135 minus 85. I guess that's 35, 40, 50.
50.
Okay, so 50 times the heat capacity of liquid, so 36.
1800.
Divide by 1,000. 1.8, right?
Mm-hmm.
Okay, that is your new x
X.
coordinate, and the new y coordinate is 135. Wait, hold on.
Like that.
Wait, that doesn't make sense. Oh, I forgot to add it. Sorry. That number, the 1.8, we add to that. We add to whatever we
Oh,
had before.
5.365. So it's 7.165.
Okay.
And then the next number is.
Oh yeah, and then the y is going to be the 130. Yeah. All right, and then they say that it ends when they reach 10. So, at this point, it's just going. It's going to, I guess. Okay, so it's already boiled, so it's gas, and then the gas. Wait, what am I talking about? Oh, I forgot to. Okay, so there's a boiling part. So this is where it turns into the gas. My bad. So this is going to be. So it's going to be the. Okay, so it's going to be what we had before, and we're going to add to that. We're going to add the enthalpy of vaporization, which is 48. So.
And more time?
So that whatever number that we had for that.
7.165.
Oh yeah, we're gonna add the enthalpy of vaporization to that number. Yeah, the 48.
$55.165. Isn't that a bit much?
What did yeah, I'm doing something wrong with the units here. Kilojoules, joules, 48. What the hell? So okay, let me go back a bit. So 135 minus that number gives us 50. Then 50 times heat capacity of the liquid is 36. And then we divided that by 1,000. And you said you got 1.8 or something? Right?
Yeah, 7.165 was the last thing.
Hold on. Let me see something. So let's see. 50 times 36 divided by 1,000. Okay, 1.8. All right, 1.8. 1.8. 1.8. Oh, we use that 1.8 number.
Mm-hmm. So 1.8 plus what?
Okay, let me see. 1.8, 1.8. Because that's 1.8 kilojoules per mole. And the number we got before that was like one point. Sorry. What was the number we got before 1.8?
You just had to use 1800 somewhere, so it was 50 times 36.
Yeah, before that calculation, what number did we get?
5.365 before we added the 1.8 in.
Okay, 5.365. Here, I'm gonna do this one more time. 1 sec. 85 minus 50 times 39 divided by 1,000. 1.365. 1.365. Then that's then 1.365 times 4. Oh, okay. All right. Okay. The number that we got was right, but it's not that the one that we graph. So this is just going to go horizontally to the right until it hits the 10.
Oh, okay, so we just go and make the lines now?
Yeah. Because the number that we got, that 55, or that really big number, that's the total heat added for this entire thing.
Like that?
Yeah, and then one more going horizontally until it hits the 10. Like the 10 right before. Yeah. So that basically means not all of it is going to boil. Yeah, I hope this is right. Awesome!
Yep.
Okay. One last time. So first we're going to do melting point, -20 minus... It starts off at -50, so minus -50, which is basically going to be 30, and it's going to be times the heat capacity of the solid, which is the 42, and then divided by 1,000. So, right?
You cut off on the last second. What was it?
Oh, so it's going to be the melting point minus the initial temperature. So -20 minus -50, that gives you 30, times the heat capacity of the solid, which is 42, and then, divided by 1,000, should get 1.26.
Yes.
Basically, kilojoules per mole. Yeah, let's do the math first, then we can put in the points.
Okay.
Okay, then it starts to actually, because I'm gonna just need to see like those numbers up top. Okay, because then it's going to start to melt once it reaches that point. So then I'm going to, yeah.
Oh. I was just making that first point.
Oh, sure. All right. Once it gets to that point, it's going to be, okay. Then it's going to be that number plus
1.26 plus.
Oh, yeah. Enthalpy of fusion.
So plus 10.
So 11.26.
Seems a bit much.
All right, you know what? All right, let's just plot the points. So, all right,
So 1.26.
So okay, yeah. So it'll be the y, okay, and then the y-axis is going to be the melting point, which is -20.
Okay.
Yeah. So that's the temperature going up, and then it's going to be like, a horizontal line until, all of it has melted.
Okay.
But yeah, I'd have to get the correct number for that. So wait. Yeah. Let me see that. Okay. 10. This is until 8 kilojoules per mole of heat has been added. So not all of it. Okay. Not all of it is going to actually melt.
Okay.
Because it goes up to 8. So, this should be. Wait, what's that other point that you have there?
Oh no, it's a glitch. It's like
Okay, because it goes all the way up to 8. So it should just be a horizontal line going to 8. Yeah, this is weird.
like that.
Yeah.
And then plotted like that.
Yeah. So the solid goes up until it reaches its melting point, and then it melts, but not all of it melts, because you need 11.26 kilojoules for that, and the experiment ends. Yeah. It looks weird. I hope. Yeah. There we go. Okay, this guy. Okay, so we're going to do 25 minus 0, which is 25, times the heat capacity of the solid, which is 43. So do 25 times 43 divided by 1,000.
1.075.
Okay, that is going to, okay, so that's going to be, so that's, and then that, okay, let me see that, sorry, yeah, sure. Let's whatever. We can plot this crap. So. Oh yeah, and then the y coordinate will be 25. Yeah. Okay, and then once it gets to that point, we're going to add the enthalpy of fusion, which is 8. So you'll get 9.075 as the new x coordinate. The y coordinate stays the same.
Can you say that one more time?
Yeah, so the new x coordinate is going to be 9.075.
Okay.
Yeah. Okay. Then, we're going to raise the temperature until it, okay, so let's see. Then the boiling point, 85 minus 25 times 59 over 1,000.
85 minus 25.
Yeah, so that's 50. 50 times 59.
It's 60.
I'm sorry?
It's 60.
Oh, crap. 60
Yeah.
times 59 divided by 1,000. 3.54.
Yeah. So first point is 3.54.
Oh, we're
And then
gonna
what's the next
gonna
one?
add that to the previous x value because it's
Oh, you
gonna.
gotta add it.
Mm-hmm.
So
So
9.075 plus 3.54.
yeah.
And then 25 again.
Oh no, now that's gonna be the boiling point, which is 85.
Okay.
Okay.
And then it's just going to continue as it goes all the way to 15.
Yeah, so it's just gonna be horizontal to fit. Yeah.
Okay.
So like x. Yeah. Yeah. Pretty much. Right before that. 15 is before that. Yeah. Cool. Amount of heat needed to melt that of that and bring it to the temperature of that. Oh, significant. Okay. But this seems to be more manageable. Oh, there are several steps here. Amount of heat. Melt and raise the temperature. Okay. Uh, so yeah, first we calculate how much energy is needed for it to melt, and then how much energy is needed for it to rise to whatever temperature they want it to rise to. So I think I can do that, and then you can make sure it's not right number of sig digits.
Okay. Start?
Mm-hmm. Okay. What? They don't even give us... Okay. Specific heat. Well, I know that for water, but... amount of heat needed to boil 138 grams of water, beginning from a temperature of 59.9 degrees Celsius. Okay. So it's like Q is equal to MCAT, kind of, that kind of thing. So it's going to be 138 whatever grams times specific heat capacity of water. What was that, like 4.18 or something?
Yeah.
Specific heat water. Yeah, 4.18. 4.18 joules per grams times, whatever Kelvin. Change in... It doesn't really... We don't have to do it into Kelvin now because it's just change in temperature, which will be the same no matter what. So, and it has to go to 100 degrees. So 100 minus 59.9 is 40.1, right?
Mm-hmm.
So yeah, you're going to multiply 138 by 4.18 by 40.1.
Say it one more time.
138 times 4.18 times 40.1.
23,131.284.
Yeah, so I don't remember if they want us to put that in kilojoules or not.
Doesn't say.
Wait a sec. Grams. So the answer for that last one was like a single digit, I think, right?
Yeah, it was like 8.1 something.
All right, and do you remember if it was like one unit, like joules or kilojoules, or like something like joules per mole?
I think it was joules.
Okay. Okay. So if it's a small number, it's probably kilojoules. So you could do like, whatever we got divided by 1,000.
23.13.
Yeah, you can do that, and whatever kilojoules. Wait. Amount of heat needed to boil that, beginning from that. It's just saying boiling. Okay, whatever. Let's try it. It might be wrong, because I didn't do anything with the moles. Yeah, damn it. Okay, So I have to do stuff with the moles now. Um, your answer is wrong. In addition to checking your math, check that you use the right data. Okay. Unit symbol, correct number of significant digits. Do I have to? Okay. $38 grams. Okay, so I don't know if they want us to do something with moles or not. If we look at the explanation, what, will that do?
It'll basically, at this point, it's probably better we do.
Yeah, okay.
Because it's not going to lose any points.
Alright, so that's that number that we got. And then, okay, that's the second step. Okay. Alright, so, let me see. I'm gonna, screenshot. Yeah, there's, okay. Damn it, okay. Oh, wait, yeah, go from, like, step 2 and, like, after, like, step 2 on the top, so I can get everything that's underneath. Like, make, like, step, yeah, like, a little bit below that. Okay. Alright. So, yeah, that was a step I was missing. So, I got it now. So, let's do it. Okay. So, we're going to do 74.9 grams times they really, okay, so like there has to be one of those things on the right, a data thing that tells us what the specific heat of ethanol is. Maybe that. Alright, I think I could Google it even faster. Oh, okay. Phase, there. Wait, I think it was like above that. Yeah, go up. Like above that. Okay, thermodynamic properties of pure substances. Let's see if ethanol shows up. Okay. Wait, where the hell? It's just Google it. Specific heat, yeah. Of ethanol.
2.46.
2.46. Okay. Yeah, forget that nonsense. Okay, and then solid ethanol to melt that of solid. Oh, the answer that we got was in liquid, I think.
Okay.
And this is solid.
Wait, what?
Here, I'll try to find some stuff. Okay, so heat. Wait. Specific heat of ethanol. Amount of heat needed to melt that of solid ethanol and bring it to a temperature of that. Okay, so I think that they mean that we just melt it first and then raise the temperature. So I'm going to do this. I'm going to find the heat of fusion ethanol. 4.9 kilojoules per mole. Okay. All right, so we're gonna do a couple of steps here. Okay, we're gonna find out how many moles that is. 74.9 grams. C, that's 24 plus 16. 20. I'm just gonna look it up because of laziness.
Mm-hmm.
Where the hell? Alright, whatever, I'm just gonna add it. 12 plus 12 plus 16 plus 6. 46 grams per mole. So 74.9 times, or divided by 46 gives me 1.63 moles of ethanol. And then I'll take the 4.9 kilojoules per mole heat of vaporization and multiply it by 1.63 moles. So this times 4.9 gives me 7.98 kilojoules to melt the ethanol. So that's that first number. Now we're going to raise its temperature to bring it to a temperature of negative 52.5. Okay, so we need to see what the original temperature was, which is basically the melting point. Melting point. Ethanol melting point. Melting point is negative 114.14. So that's where it starts, and we're raising it to negative 52.5. So minus negative 52.5. So basically 52.5 minus 114.14. Get negative 61.64 for delta T. So now I'm going to do 74.9 grams of ethanol times specific heat of ethanol, 2.46. Wait, that was in...
Yeah, it was 2.46.
That was in joules, right? Okay. So I'll have to do that. All right, then times...
You want it in kilojoules?
No, I could just divide it by 1,000 at the end. So 61.64 divided by 1,000. I get 11.36 kilojoules. And then if I add that to the 7.98, I get 19.337. So yeah, that's what I got.
Say it one more time.
I get 19.337, which could be, I guess, 19.34. I don't know.
I'll try 19.3 first.
Okay, kilojoules. All right. I hope this works. All right. Yeah, that was a lot of calculations. Okay. And a lot of stuff we have to look up too. All right. Amount of heat needed to boil. Same thing. Thank God. Okay. Beginning from a temperature of this. Okay. Let me look at the boiling point. Okay. Boiling point is positive 78.23. So it starts from a temperature of negative 76.8. So the change in temperature is going to be 78.23 plus 76.8. So that's 155.03. Okay. Okay, and then so I need the heat. So there's basically two heats here. There's a heat added to raise the temperature, and there's a heat that's added to make it boil, right? So the heat added to raise the temperature is going to be the mass, 171 grams, times the specific heat, which was 2.46, times the change in temperature, 155.03. So this times 2.46 times 171 is then divided by 1,000. So 65.21 kilojoules. So that's to get it to that temperature, its boiling point, and then the amount needed to boil it. So that is going to be the heat, like capacity of the ethanol thing. Okay, so let's see. Oh no, rather the heat of vaporization for ethanol. That is, well, okay, alcohol. Okay, so okay, that's 0.826 kilojoules per gram. Wait. It's usually in per mole. Okay, 43.5 kilojoules per mole. And we have the same mass, so it should be the same amount of moles, which is 1.63 moles. So 1.63 moles times 43.5 kilojoules per mole is going to give us the energy for that. Okay, so 1.63 times 43.5. So that's 70.905 kilojoules. We add these guys, so add that to 65.21. I get 136.115 kilojoules.
So it should just be 136. Check.
Yeah, I hope so. Oh, I hate my life. Okay. Oh man, it's a different mass. I used the same mass as before. My bad.
Oh,
I used, okay, so 171 grams divided by 46. Okay, sorry, 171 divided by 46, 3.7. So 3.7 times 43.5. So that's 161.7 plus 65.21. Okay, it's actually 226.9. So like 227. All right. Wait, did we get that one? 208? What did I do here? I was off by like a little bit. 3.7 moles. 38. I guess I got a different value for the molar heat of vaporization. And let me see that first step. That step 64 point. How did I get? I got 65 point something. What did I do? 2.46. The 155 I got. The 2.46, it's 2.438. I'm off by like a little bit because I got used numbers that I got from Google. So we have to use their values.
okay.
Because we were off by like 20, like 18. So we have to use their stupid numbers. Okay. All right. Okay, dude. All right. Let's do this. What is this? Is for benzene. So I'm basically going to need the specific heat and the. All right. So they're saying melt. Okay, so I'm going to need the heat of fusion and the specific heat for benzene. So yeah, we're going to go to basically like the phase change stuff. Okay, so let's find. Okay, there. All right, not bad, not bad. Okay, so this is. All right, specific heat capacity 1.741, and the heat of fusion 9.87. Okay. And they have to be like assholes about making the heat of fusion like in kilojoules per mole, and then the specific heat like joules. So okay. Benzene is 6 times 12, 72 plus 6, 78 grams per mole. Okay. So we melt it first, and then we bring it to that temperature. Okay, so I'm going to need the melting point too then. Melting point of benzene, 5.538 degrees Celsius. Okay. All right, okay. So, okay. First step, we take 160 grams of solid benzene. We multiply it by the specific heat of benzene, which is 1.741 joules per grams times Celsius. And we multiply it by the oh wait, crap. We melt it first. wait, JK. So melting it first means that, okay, I have to change it into moles. So 160 grams times, or divided by 78 grams in a mole. So 160 divided by 78 is equal to 2.05 moles. So 2.05 moles of benzene times the heat of fusion of benzene, 9.87 kilojoules per mole. So this times 9.87 is 20.246 kilojoules. Okay, that's the first number. And then the second number is the 160 grams times 1.741 specific heat, and then the change in temperature. So that'll be 68.6 minus the melting point, 5.538. So change in temperature, 63.062. Okay, that times 1.741 times 160. I get, and then divided by 1,000. I get 17.5665 plus 20.246. I get 37.8125. Okay, that should be it.
One more time.
37.8125 kilojoules. Yeah. That's another one of these messes. Okay.
Methanol.
Methanol, okay. The
2.531.
sorry, wait. Let me just get, okay, the melting point is, oh wait, boiling point, sorry. Boiling point, heat of vaporization and specific heat. That's what I need for methanol. Okay, so that 2.531, is that the specific heat?
Yeah. And the other one's heat of fusion.
And, oh no, so I need, since it's boiling, I need the heat of vaporization. Yeah, that one. So 35, right? 35.21 kilojoules per mole.
And the specific heat was 2.531.
Yeah, and then the boiling point is at the 64.5.
Mm-hmm.
Yeah. Okay, now let me just do the molar weight. Molar mass, 12 plus 16 plus 4. So 32 grams per mole. So let me just find the moles. Okay, 28.2 divided by 32. Whoops. So 0.88 moles of this crap. Okay. So it starts at that temperature and until it reaches its boiling point. Okay, so Q is equal to 28.2 grams times specific heat, 2.531 joules per gram times Celsius times delta T. So starts at negative 15.5. It gets to 64.5. So 80 degrees Celsius. Now this gives me, so 80 times 2.531 times 28.2 divided by 1,000, 5.71 kilojoules. So that's to bring it to the boiling point. And now the energy to boil it is going to be 0.88 moles times 35.21 kilojoules per mole. So 0.88 times 35.21 is equal to 30.98 kilojoules plus 5.71 kilojoules. Answer should be 36.69 or like whatever, 37, whatever, I think, kilojoules.
And one more time.
36.7 kilojoules. Yeah. Oh my god, more. Okay, so let's, yeah, okay. $196 grams of methanol. Oh, it's the same crap. Okay, so now it's going to be the melting point is negative 97.5, and the heat of fusion, right, is going to be
3.215. And that's in
yeah. So 3.215. Okay. Okay. So okay. The heat caused by melting it, so 6.125 moles times 3.215 kilojoules per mole. 6.125 times 3.215. 19.69 kilojoules. Then we're going to raise its temperature. So what, we got 196 grams times that specific heat was 2.531 joules per gram Celsius. Times the change in temperature, so that's going to be negative 97.5 minus negative 5. Wait, no, minus. Wait, yeah, minus negative 5.1. Uh, 102.6.
Which means 102. Or 103.
Yeah, I have to pick up a package downstairs. I'll be right back.
It's wrong.
Okay.
It's
Wait. That's not the answer. That was just the change in temperature. So 102.6. Oh, you tried it? No, sorry, dude.
I thought you said it was the answer.
Oh no! I was just getting the change in temperature. And then I had to pick up like a package. So here, that times 2.531 times 196 divided by 1,000. So that's 50.89. So that plus 19.69, 70.587. That's going to be your answer.
$75.587?
No, 70.587.
So 70.5 then.
0.6. Whatever. Jesus!
65.5. Oh my god.
What did I do here?
To get 3 of these right. Oh my god. Subject.
One of them have to be an... What? Oh. Yeah, I see what I did. Oh, yeah, we're doing different stuff?
Do you want to keep going with that one or something different?
All right. Let's finish. Let's just do it.
All right. Let me go back to it.
I think I know what I did with that one.
Okay.
Wait, let's
Let me
see.
get your hex in.
90.5 minus 5.1.
So heat of vaporization and specific heat are here. Specific heat 2.27.
Was the answer to that one? What was the answer for that one? Was it 64?
The last one?
Yeah.
65.5.
All right. Yeah. All right. I see what I did. I just got that. Oh man. Ugh. I added the negative 90 thing to the 5 thing instead of subtract. Okay. All right. Let's. Yeah. I'm gonna get it all this time. So 119 grams of hexane. Let's see. Hexane and boiling. So I guess the boiling point is 68.72. The heat of vaporization, 28.85 kilojoules per mole. And specific heat is at 2.27.
Yes. And the heat of vaporization is 28.85.
Okay. And then 72 plus 14, 86 grams per mole. So 119 divided by 86, 1.38 moles. Okay, that's all the information I need. So amount of heat needed to boil this, beginning from a temperature of that. Okay. So, that's pretty close to the boiling. The boiling point is 68.72, right?
Mm-hmm.
Hexane, 68, okay. 68.72 minus 64.2. So we got 4.52 times 2.27 times 119. And we got 1.38 moles times 28. Oh yeah, I have to divide that by 1,000. And then, okay, so 1.38 times 28.85 will give you that, and we just add these guys. Okay. So 4.52 times 2.27 times 119 divided by 1,000, 1.22. Then we got 1.38 times 28.85, and we get 39.813 plus 1.22, 41.033. Answer should be 41 kilograms. Kilojoules.
41.133 was the thing?
I got 41.033.
Check.
Yeah.
Okay.
Okay. This crap again. So 115 grams methanol, and I just need to see if it's like boiling or heating or whatever.
Yeah, just trying to get
Yeah.
It's melting.
Okay,
And
so
it's
heat of
45.3.
fusion, specific heat, melting point, and that's 12 plus 16 plus 4, 32 grams per mole. 115 divided by 32, 3.59 moles. Okay, so yeah, let's see, methanol. Yeah, show me methanol. Okay, so this guy has a melting point of negative 97.5, specific heat of 2.531, and heat of fusion of, what is that, 3.215?
3.215.
Okay. All right, so 115 times 2.531 times, okay, I gotta not mess up this temperature thing this time. So final minus initial. So final is a melting point. So I'm gonna put in the negatives this time. negative 97.5 minus negative 45.3 gives me negative 52.2, but we're not going to keep it negative. Okay, so that times 2.531 times 115 divided by 1,000, 15.19. Okay, then 3.59 moles times 3.215, 3.59 times 3.215. I get 11.54 plus 15.19. I get 26.73.
Say it one more time.
26.73.
Kilojoules, right?
Yeah.
One more. Hexane.
Okay, this thing. Yeah. See if you can lower that window a bit so I can write it like some info down as you go to that. Okay. 42.8 grams. And so boiling point, specific heat, and heat of vaporization.
28.85.
So hexane, what is this? Okay, boiling point of 68.72. Specific heat 2.27. And heat of vaporization 28.85. Okay. So it begins at negative. Okay, so final minus initial 68.72 minus negative 19.1. So delta T is 87.81. I mean 82. So we're going to do 42.8 grams of hexane times specific heat. Wait. Okay. Times specific heat times the change in temperature. This times 2.27 times 42.8 divided by 1,000. You get 8.53. Okay, then I do the 0.49 moles times the heat of vaporization, 28.85. So 28.85 times 0.49, 14.14. Add that to the 8.53. I get 22.67 kilojoules.
22.67?
Yeah.
22.6. That's correct?
Yeah. If this is wrong, I'm going to be upset. Yeah! Oh my god. What did I do this time? Jeez Louise. Okay, we can do this. Okay. So molar mass 6 times 12 plus 14 is 86. 42.8 divided by 86 gives me 0.49 moles. Okay, and yeah, the boiling point is 68.72, and I subtract it by the starting temperature of 19.1, I get 87.82. I mean, these numbers are right. Let's check like the, whatever the heat of stuff. I just want to make sure about that, because wait, I don't know what I did over here. Times 2.27.
At specific heat.
Yeah, times 42.8 divided by 1,000, 8.53. Yeah. So hexane 68.7.
Did you use heat of vaporization?
What's up?
You used the heat of vaporization, right?
Yeah, 28.85.
We need it to boil, so that's heat of vaporization. Oh.
Amount of heat to boil that much of hexane beginning from a temperature of this. I'm really... I mean, if it's 22.66 and the answer is 22.7, would it think that it's wrong? Like, what?
I'll try it.
Because that wouldn't that round to 3 or 22.67 or 22.7?
Usually when I put it in like this, it's always correct.
What if it? But like if it's off by a tenth, like if it's 22.7, would it still take that as an answer?
Let me see.
Okay. Oh, Jesus. Better not be some negative. Oh, wow, really?
22.9.
Really? They suck. What the hell?
I hate this system. This Alex thing is the worst thing ever.
We were off by 0.2.
And it couldn't even take it or tell us that we're just off.
Yeah.
It took off the entire.
Jesus. All right. Okay, we're gonna do it right this time because we're gonna put in the full values and stuff. So okay, like, all right, heat of fusion, melting point. So where's that? So I need that stuff.
Hmm?
Oh yeah, oh yeah, sorry, you have it there. Okay, heat of melting point is negative 97.5. Heat of fusion, which one is that again?
It's gonna be this one.
3.215, and then specific heat is
2.531.
all right. Then methanol was 12 plus 16 plus 4, 32, and this is 139 grams. I'm gonna write every digit down this time. So this is 4.34375 stupid moles. Okay. So melting it and bringing it to that temperature. So first, that's 4.34375 moles times heat of fusion, 3.215, is 13.96515625. Okay, then change in temperature, 40.8 minus the negative 97.5. Final minus initial. Delta T is 138.3. So this is going to then be 139 grams times specific heat, 2.531, times 138.3. No, divided by 1,000. So, okay. That's times 2.531 times 139 divided by 1,000. You get 48.6551847 plus 13.96515625. You get 62.62034095. So, whatever.
62.6 was the first three digits?
Yeah.
One more.
We've done like 10 of these. Jesus.
I know.
Yeah. Okay. Okay, 167 grams of hexane. And it's boiling. So I'm just going to rewrite everything. Heat of vaporization, boiling point, specific heat. So let's see. Hexane, boiling point 68.72. Specific heat 2.27. Heat of vaporization 28.85, right?
Yes.
Okay, we got 1.94186 moles. Delta T, that's going to be final. Okay, so 68.72 minus 70.3 negative 139.02. Okay, so we got boiling it first, and then wait. No. Raising the temperature first, and then boiling it. Okay. So 167 grams times 2.27 times 139.02 divided by 1,000. So this times 2.27 times 167 divided by 1,000. 52.7010918. Then the next one is 1.94. Oops. 1.94186 moles times the heat of vaporization, 28.85. Okay, 1.94186 times 28.85. 56.022661 plus 52.7010918. 108.723 blah blah blah. So answer should be, yeah, whatever significant figures that is.
1 point what?
Oh, sorry, 108.7237. Yeah, I hope that was last. All right. Jesus. That was killer. Enthalpy of vaporization is that. Calculate the vapor pressure. Yeah, you're like F this.
Lesson 1. This is ridiculous.
This sucks that the class is just all through like this Alex thing.
Well, that, and it's also, what do you call it? Oh my god, what's that thing? It's also this stuff over here.
Yeah.
I know I'm gonna get this done in 20 days.
What, 253 of these?
Well, not just that.
Yeah, this is torture.
Fucking 12 of this thing. Why is this recharge? She needs to fix the due date on that. Shit, goddamn.
Are we doing this?
Yeah.
Okay. Jeez. All right. Calculating the vapor pressure. Oh man, this is some Euler's number stuff over here. Clausius Clapeyron. Okay. Jeez Louise. Okay. Oh my god. Okay. Let me write this down. Pressure 1 over pressure 2 is equal to Euler's number to the power of the heat of the enthalpy of vaporization over R times 1 over T2 minus 1 over T1. Jesus. Keep an extra 2 digits. And then you have to put it in Kelvin too. Yeah. See what if you can scroll down what so anti-log. This is nightmare. Okay. Make sure. Okay, so this thing is in kilojoules. This thing is in joules. And pressure is in ATM. Okay. Let's do this. Okay. Okay. All right, T1 is 103 plus 273, so 376 Kelvin. T2 is 28 plus 273, 301 Kelvin. Okay. Enthalpy vaporization is 29 kilojoules per mole. Okay. Ideal gas constant is that. And okay, it's the vapor pressure at the normal boiling point would then be just 1 atm, and we have to solve for P2. So yeah, what a disaster. Okay. All right. So 1 over 301 is equal to, so okay, I think I'm gonna need, because there's gonna be, I can't, hold on, let's see if I can do this with parentheses 1 over 301 close parentheses minus open parentheses 1 over 376 close parentheses. Okay, so for that part I get 0.002659. Okay, and then then the heat of vaporization over the so I'll just turn the thing into kilojoules maybe. So 29 kilojoules divided, 29 divided by, so this is just 3, you know, I'll just turn the kilojoules into joules. So 29 with 1,000 after it. 29,000 divided by 8.3145. Okay, so then I get 3,487.8826. Multiply that by 0.002659. I get 9.274278. Okay, that should be that top term. And then I have to do e to the power of this number that I just got. That gives me 10,660.2790. That seems extremely high. Wait, hold on. Oh, okay. Hold on. Because I need to get P2. So I have to divide it by that. So 1 over this, then. Hold on. So P2 P1 is 1 atmosphere, 1 over this number. I don't even have the answer thing on this. Whatever, 10,660.279. I think I got an answer. Maybe it's 9.38.
If you can't get this one, we'll just what do you call it? Pick up next time. We're out of time.
Okay, maybe I had to do the anti-log. Oh, I should have done the net. Okay, let me see something. Okay, I could take the natural log. Okay, so that answer I get is this. And I could take the natural, okay, so natural log of P1 over P2 is equal to this number, 9.27, blah, blah, blah. Okay. Then I can do, oh, and it's a negative? I forgot to put that negative there. That changes everything. So, okay, then it'll be just this thing, but negative. Okay. Okay, I'll do, okay, the anti-log of this. So 9.27. Where's the anti-natural log? I mean, where is it? Okay, this number. Damn it. sure there's some calculator. Okay, I'm just gonna put it into this calculator I found online, because F this. Okay, initial temperature. Wait. This is kilojoules. 29. Okay. Try point. So I try 0.09. Well, I get 0.09933. All right, awesome.
Yeah.
All right, I'm gonna put it into this calculator. 27.
We're out of time.
What's up?
We're out of time.
Okay, I can do this like wait. Try 0.40.
Hmm?
Oh, try 0.40. Like 0.4.
Okay, try it.
Yeah.
Yeah?
Yeah.
Okay.
Yeah. And then we can finish it on this one. Try 0.35. Well, I get 0.3548, so whatever that turns into.
Yeah, 0.35 because it's 2 sig figs.
Okay. Yeah. All right. That was a good way to end it.
Yeah. Okay. I also gave you my login information, right?